Hey there, in this video we are going to look at transformations of logarithmic functions. Or in other words, we're going to apply translations, expansions, compressions, and reflections to the graphs, and we're going to see how that's connected with changes to the parameters in their equations. So before we start looking at transformations of logarithmic functions, I'm going to make the assumption that you've either watched my previous video or you've learned elsewhere about basic logarithmic functions, like the one that's on the screen here, which is y equals log base 2 of x, about why they look the way they do, some of the features, as well as how changing the base, b, affects how the graph appears, which is what I'm doing here, changing that base. And you can see that either it goes up to the right if that base is bigger than 1, or down to the right if that base is smaller than 1. But for more detail on that, of course, watch the previous video. Now, I'm also going to make the assumption that you've learned about how changes in the equation affect transformations in the graph for functions in general, either from my set of videos on transformations of functions in general or elsewhere. So then, given all that, we're going to look at applying those transformations that I mentioned earlier to logarithmic functions. So things like horizontal translations, vertical translations, vertical expansions or compressions, and then reflections. All right, we're going to look at that in several different ways, and we're going to start that right now. Now, we're not going to go too overboard with the number of transformations we do here with logarithmic functions. We may do 1 or 2, not to the extent you might have done when you worked with transformations of quadratics or trig functions, or even exponentials for that matter. So the first thing we're going to do is look at a pair of equations and identify what transformation has happened. So in this first part here, we have our base function is log base 7 of x. And if we make the change to y equals log base 7 of x minus 3, or in other words, if we change x to x minus 3, what that causes is a horizontal shift of 3 to the right. X to x minus 3, shift of 3 to the right. In the second one here, our base function is y equals log base 4 of x. If we change that to y equals log base 4 of x plus 4, now this is important to recognize, this is not like this. It is not making that same change as in the one above. This is, if you had to have some brackets on there, it would be like that. And when you add or subtract a number onto the end of that function, you're actually going to cause a vertical shift, and in this case it's 4 units up. In our third one here, we have log base 1/9 of x, and that gets changed to 4 times log base 1/9 of x. If you take a function and you multiply it by 4, that is going to cause a vertical expansion by a factor of 4. All the y values are going to be 4 times as much. This fourth one here, part D here, log base 9 of x, getting changed to minus log base 9 of x. That negative in front of the function, or in other words, multiplying the entire function by -1, causes a vertical reflection over the x-axis. And then this last one here, when we change log x to log negative x, or in other words, we replace x with negative x, that causes a horizontal reflection over the y-axis. All right. All right, next we're going to sketch the graph of a couple of transformed functions. The first of which we have here, log base 2 of x plus 5 minus 4. There's a couple of transformations that have happened there. The fact that this is x plus 5 in here instead of just an x means that that has had a horizontal shift, horizontal translation of 5 units to the left. And then the fact that there's this minus 4 on the end, it has had a vertical shift 4 units down. And the way we're going to handle that in drawing this graph, you could actually do kind of a couple things here. You could draw the base graph log base 2 of x and then draw each step of the way. First, shift that graph 5 units to the left, then shift that graph 4 units down. That's a lot of graph drawing. What I prefer to do is identify those two shifts as in the axes are going to move and then work from there. So what I mean by that is, if we're going to shift this whole graph 5 units to the left, that is going to end up right here. So I'm going to put a dotted line right there, and that's going to be where I'm going to work from. And then for 4 units down, that is going to end up right here. So I'm going to put a dotted line there as well. Now I'm going to work from there, and now what I can do is just kind of ignore these two things. I can just graph y equals log base 2 of x from there. And so if we were graphing it from the origin up here, if it wasn't shifted, we'd have log base 2 of 1 is 0, log base 2 of 2 is 1, log base 2 of 4 would be the next one you could do nicely, which is 2, and so on. We're going to just do those things, those points, from down here. So what I mean by that is log base 2 of 1 is 0, log base 2 of 2 is 1, log base 2 of 4 is 2, and we can fit in 8 as well here. So if I go 8 squares there, right, that would be 8 is going to be 3. 16 would be the next one. It's going to be off our grid, so I'm going to leave that alone. The other side's a little harder, but we could go log base 2 of a half is negative 1, and log base 2 of a quarter would be negative 2, and that's probably enough in there to get the shape right. So I'm going to draw like this, as smooth of a curve as I can, and then just draw it kind of asymptotic along that line there. Put an arrow to say it keeps going at each end like that. That's our graph. All right. Working with that second one, y equals negative log base 3 of x minus 1, identifying there's a couple of transformations here as well. First of all, there is a vertical reflection because of that negative in front of the whole function. And because of that x minus 1 in here, there is a horizontal shift of 1 to the right. Now, really, the order of the transformations is this happens first, and then this happens second. But what I'm going to do is put a dotted line to account for this, and then just draw the reflected graph there. Also, these are one in a vertical direction, one in a horizontal direction, so it actually doesn't make a difference which way you do it. So horizontal shift of 1 to the right, I'm going to put a dotted line right there and use that. And then I'm going to draw the graph of this. Log base 3 is going to be the same as always here. Log base 3 of 1 is 0. Log base 3 of 3 would normally be up here 1, except I'm doing this vertical reflection, so instead of up above there, I'm going to put it down here. It's going to be below, right? And then the same thing. Next nice point I can do is log base 3 of 9, which is going to be right there, 9 squares over there. Again, normally that would be 2, but it's reflected, so I'm going to put it down below here, negative 2, like that. And then we could do log base 3 of 1/3. Normally that would be negative 1, but again, reflected, so it's going to be up above there at positive 1. And then that's probably enough to get the shape right. I'm going to just draw a nice smooth curve through this whole thing here as well, those 4 points. And then again, it's asymptotic there, and I'll do my best to get closer all the time, but not touch it or cross it like that. And then put an arrow on that end as well. All right, there's those two graphs. The next thing we're going to do here is take a graph of a transform function and write an equation for it. In this first one here, we have this dotted line as the original graph, and this blue graph here, solid line, is our transformed graph. Now, it might not be easy to tell because it looks like it's farther apart here than up here, but what has happened is actually it's been shifted 3 units to the right, and you can tell if you pick any specific point here, you see that's 3 units there, that's 3 units there, this point right here is 3 units, and so on. That's even 3 units. It's just so hard to tell because the slope becomes kind of shallow there, but the whole thing has been shifted over 3 units, and that's actually all that's happened. So you need to know that, the fact that it's been translated 3 units to the right, but you also need to know the base of the function, and you can get that, the base of the function, just by looking at the values here from the axis. That's 1. This next one is 2. Here you have 4. And here you have, if you count those off, that's 8. So in that case, you have that the base is 2, right? And then we said also that there's a translation of 3 units to the right. And so to put that equation together, it's going to look like this. Y equals log base 2 of x minus 3, right? The base is there, and then instead of x, you've got an x minus 3 there, all right? Let's do this second one over here. In this case here, it's pretty clear that this has been shifted down, right? The dotted line's been shifted down, and you can tell by picking some points that correspond to each other here that that's been shifted down 4 there. You can just confirm that it's a shift instead of some other kind of transformation, that every single point there has been shifted down. Pick any point on that curve, and there's going to be 4 units to there. So you have this vertical shift 4 units down, and then we also, of course, need the base of the thing. And the way you can get the base is just have a look at the values here. So on our original curve here, that's 1, right? That's a 1 there. And this is a 7. We don't have another one to go on here because this is off the graph, but we can use those two to decide that the base is indeed 7 there. All right, if you've got 1, 7, the next one would be 49 if we had the grid that far. And then we said we have our translation of 4 units down. So if we're going to write an equation for that, it is going to look like this. Y equals log base 7 of x minus 4. And again, this is not brackets like that, because that would be a horizontal shift. If you wanted to put brackets, you'd have to put them there, just to say for sure that it's log base 7 of x, and then the minus 4 is outside of that log function, which causes that vertical change. All right, let's look at 2 more. Okay, in this third one here, we have our original function there, and we have our transformed function here. And if you look at it, it certainly looks like this is not a translation. It hasn't just been shifted. What's happened is it's been reflected, right? Any point that is above here is now below, right? This point, let's say right here, that point that's 2 above is now 2 below there. And any point that's below is now above. That has undergone a vertical reflection. And then we also need to know what the base is. So if we look at our original graph, again, we can get it from just looking at some of the points here, the pattern in the points. We've got 1 there. We've got, that's a 3. This is a 9 right there. 1, 3, 9. That sure sounds like the base is 3. And then we said we have a vertical reflection there. So if you're going to put that together to write an equation, we need log base 3. And then to get that vertical reflection, we need this negative in front of the whole thing. All right. Let's look at this fourth one here. We have our original graph right there, and we have our transformed function right here in the solid line. There's actually a couple of things that have happened there. First of all, instead of it curving off to the right here, it curves off to the left. There's been a horizontal reflection. And then also this asymptote, which is normally right there, is way over here at 7. So we've had this shift of 7 units to the right, a horizontal translation. And then of course we need the base, and again we can figure that out by looking at some of the points on the original here. And it's easiest to look at this here, right? That's a 1 there, and then our next one is, looks like to me that that's a 5 there. And again, this next one would be off the graph over here, but if we have 1, 5, we can tell that the base is 5, right? And then the next point here, that would be 25 off of there if we had it on the grid. So from that we can write the equation. We need to have both of those things accounted for, and our equation is going to look like that. All right, we've got log base 5, and the 2 changes are both horizontal, so they're inside where the x is, and you've made 2 changes. We need this negative in here to cause that horizontal reflection, and then replacing x with x minus 7 causes that shift of 7 units to the right. It needs to be written in that factored form like that. You couldn't eliminate these brackets and that would be something different, right? In your standard form, you have it in that factored form inside there like that, all right? All right, so to summarize what some of the parameters in that transformed log function do, the first one, this a value in front here, that is the value that causes a vertical expansion if the value, the number part, the absolute value of that number is greater than 1, and if the absolute value or then just the number part is less than 1, it's a vertical compression. And then we also have a vertical reflection if that is a negative in front there. We didn't do any combinations of those two things, but both of those would happen if you have a number that's less than 0 like that, if it's a negative number. And our second value over here, well, b is the base of the logarithm, as you've seen before. If you watched the previous video about basic logarithmic functions, you know that the graph goes up to the right if that b value is greater than 1, and you know that the graph goes down to the right if the b value is less than 1 and bigger than 0. And again, if you watched the previous video or you've worked with logarithmic functions before, you know the base has to be either greater than 1 or between 0 and 1. It can't be 1 and it can't be negative. Our third parameter there, c, inside there, that causes a horizontal shift. If the value is positive, the shift is in the negative direction. It does the opposite. If the c value, if it says x plus 7, it's 7 in the negative direction. And then if the c value is negative, it goes in the positive, goes to the right. All right, and then lastly here, our d, which this is going to be off the screen as I talk about it, but that value on the end there, that value causes a vertical shift, and if that value is positive, greater than 0, the shift is up, and if the value is less than 0, the shift is down. All right? Now you might notice up here that in our general equation, you don't have all the parameters that you might have seen before. With other functions, we have this c in here, which is connected to horizontal translations, or this d out here connected to vertical translations, and of course the a in front connected to vertical expansions, compressions, and reflections. What I don't have in here is a value in here that multiplying that x that would be connected to horizontal expansions and compressions. And the reason is because there's some interesting things that happen specifically with logarithmic functions where a change of one kind in a graph can actually be represented a couple different ways in the equation. And I'm not going to say any more about that because that is the subject of a future video. But I just wanted to mention that in case you're wondering why that is missing there. Before we're done here, we're going to look at just a few last things. First of which is which of the values affect where the asymptote is located. The value of c is the value that affects where the asymptote is because the asymptote is a vertical line, and so a horizontal shift, which is what the value of c does, is what changes where that horizontal line is. And secondly here, which of the values affect where the x-intercept is? There's actually two values that affect where the x-intercept is, and those are c and d are going to affect the location of the x-intercept because both of those types of shifts, horizontal and vertical, are going to cause the x-intercept to move. With shifts, every point on the graph moves. So if you shift it vertically or horizontally, you can see that the x-intercept is changed. Thirdly here, what happens if a has a negative value? If a has a negative value, we saw that it was a vertical reflection, and the reason is because all the y values will change signs. Whatever y values were positive become negative, whatever values were negative become positive. Next, which values affect the domain of the function? The domain of the function is going to be affected by the value of c. And the reason for that is because that's the one that affects where the asymptote is, and the asymptote marks the end of the interval that the domain is. So that value of c affects the domain, where the domain starts. And then next here, do any of the values affect the range of the function? And the answer to that is nope, none of them affect where the range is because the range is all real numbers. And so making any changes, the range for any of those values, the range is still going to be all real numbers. And then lastly here, how are the location of the asymptote and the domain related to each other, and I alluded to that just a second ago, that the asymptote is located at the end point of the interval of the domain. The domain starts at the location where the asymptote is. All right? So that is a look at transformations of logarithmic functions.